to this computer. Okay, hello everyone. Welcome to ARMA Future Leader webinar series. Today is our last Future Leader webinar for this year. Dr. Tingting will bring us this mutual scale modeling of coupled mechanism in geomechanics. Dr. Xi is a postdoc fellow currently affiliated with the Hopkins Extreme Material Institute at Johns Hopkins University. She worked with Dr. Vicky Wing on polymer mechanics and Dr. James Guest on topology optimization. In spring 2025, she will join the Department of Civil Engineering at McMaster University as a tenure-track assistant professor. Prior to join Johns Hopkins University, Tingting earned her PhD from Georgia Institute of Technology under the guidance of Dr. Chloe Arson, focusing on multi-scale modeling of multi-physics process in geomaterials. She also holds a master's degree in computational science and engineering from Georgia Tech. Okay, let's give time to Tingting.
Okay, thank you. Let me share the screen. Okay, so everything is good, right? You can see my screen.
Yeah.
Okay.
Can you speak a little bit louder?
Oh, probably the mic is far away. Is my voice clear right now?
Yeah, okay. Thank
you. Thank you. So right now I'm the postdoc in Johns Hopkins University, and my research area is, as Qichen just said, it's focusing on the polymer mechanics and topology optimization. So which I believe is quite different from the rock mechanics. So I really appreciate this opportunity to take me back from the polymer mechanics to the rock mechanics. So the topic today and the work that I can present today is a work that I have done in Georgia Tech during my PhD, working with Dr. Chloe Arson, and some following work that I finished recently. So the topic today is a multi-scale modeling of coupled processes in geomechanics. And this is a quite broad topic, but my main focus in this study is a homogenization scheme. So for the composite material. So we would encounter different composite materials in our life and also engineering application. It's including like a natural composite material such as the soils and rocks in the geomechanics, and probably some concrete material in the structural engineering, and also the tissues or the soft matters that in the mechanical engineering. So it's kind of, I have a different types of the composite materials. And here is an example of the concrete. So from the left figure, you can see that it is a microscopic image for the fiber reinforced concrete. And we would imagine that the fiber alignment and the property of this fiber will influence performance of the fiber reinforced concrete in the laboratory. So understanding the response of the response or the behavior in the laboratory will also help us to assess or evaluate the performance of these retaining walls or large scale structures at the structure scale. So that's tells us how it's quite important to us to understand the microscopic behavior and understand how it linked to the microscopic behavior for this composite material. And with all this understanding, it can help us to assess the integrity of all these structures or for in the real life in the larger scale. So before moving into this multi-scale modeling, I would very briefly introduce the concept called the representative elementary volume. So that is sometimes we call it REV or RVE, that represents the smallest size of the specimen that can take to be considered statistically representative of the material. So this concept or the actual size of this REV really dependent on what kind of property that we consider for this material. So in this slide, I show the example such as the porosity. So you can see the porosity defined as the volume of the pore divided by the volume of the, the volume of the pore divided by the total volume. So you can see that with the different size of the windows, we can take it and we calculate the porosity of that. And from the right figure, you can see that to some extent or to some size of this window, the porosity of this calculated porosity won't change, and it coincides with the total porosity of the specimen. So at that size, we could say that, okay, this size of the window, this size of the small piece of the of this volume will be representative. So that is the size of the REV of this specimen that is corresponding to the property that is porosity. Of course, with the different properties that we want to consider, we're going to get a different size of the representative elementary volume. So our study is focusing on how to link the behavior of the microstructure to the behavior of the representative elementary volume. So here it's a sketch of it, the scale separation of the three different scales that we considered. From left to bottom, we have the smaller and smaller scale. And left figure is a boundary value problem that we probably want to solve in a larger scale. And the middle column of the figure is a REV, the representative elementary volume. And the right figure is a microstructure. So in order to link the microstructure behavior to the REV behavior, we sometimes will have two categories of the models. The first one is a phenomenological model that we consider the internal variables as a scalar or the tensor, more complicated tensor, such as the porosity, the cracks, the mineral types, or the lattice orientation. And we use that to cast into our traditional like elastic model or elastic damage model, elastic plastic model, or even the viscous model. And we use that phenomenological model to describe the response or the behavior at the REV scale. And on the other hand, we also have so-called the micromechanical model that we can consider the local behavior or the local constitutive model or the local relation between the stress and strain at different locations. And then we use a relation to link this local constitutive behavior to the REV constitutive behavior. So that can give us more information than the phenomenological model, which is also the focus in this study. So before going into the homogenization method, in this study, I want to introduce like the full field homogenization method. So with the development of the different numerical tools, we usually see that, okay, we probably want, if we want to solve the boundary value problem in the solid mechanics or the rock mechanics, we usually use the finite element solver. And in order to get the response at each integration points to simulate the finite element simulation, we probably can get it from a different numerical tools, such as the finite element simulation. So it's known as the FE square, or from the discretized element simulation. So that is FEM and DEM coupling. And sometimes we can also use the fast Fourier transform. So that is FE and FFT coupling. So with the different numerical tools, we can get as many details of the microstructures as we can. And we can simulate that, capture the behavior of the REV But on the other hand, you can imagine that with all these numerical tools, this is quite computationally expensive. So usually it will take a lot of time. And sometimes we can also use the machine learning tools to train all this simulation and bypass all this time-consuming simulation right now. So that is kind of like summation of this summary of the full field homogenization. The method that we used in this study, we call it the mean field homogenization. So you can see that instead of using a different numerical tools, which is time consuming, we consider the micro to macro transition as the integration of the effective quantities. So if you look at the equations here, you can see that the effective quantities of the whole REV can be considered as the volume integration of these quantities. So we will have if we consider the large strain or the finite strain, we will have the kinematics and kinetics. We can take the deformation gradient as the volume average of the local deformation gradient, and also pk straits as the volume average of the local pk straits. And also, if we consider small strain, we can of course take the strain and the caustic straits. So with that understanding, we can pass the stiffness tensor and straits into the integration point, into the REV behavior, and we use that behavior to do the finite element simulation. So this definitely couldn't capture as many details as we used. I just introduced in the full field homogenization. But on the other hand, it's not that time consuming because it has the analytical solution, and we simulate that. We can capture some information of the microstructure, and we can save some computational time. So that is the main focus in this study. I would take two different examples to explain this homogenization scheme. The first one is a soft rock. So here is the motivation why we want to investigate the soft rock. It is a quite interesting material because it has a high thermal conductivity, low permeability, and most importantly, it has a self-healing mechanism. So it is a very good material for the storage, waste storage. And here, before we go into the actual model, we usually want to ask ourselves the questions: which deformation mechanisms should we focus in our study? So that really influences how we pick the representative elementary volume. So in this study, we have two main deformation mechanisms we want to consider. The first one is a dislocation creep. So it is a time-dependent behavior that happens inside this crystal. And the second one is a so-called pressure solution. So the pressure solution is the chemical reaction, and you can see that under the compression from the sketch at the right bottom, you can see that under the compression, there are two grains that contact with each other, and a solid will dissolve under this compression force, and then the ions will diffuse along this contact boundary. And the third step is that the ions will precipitate on the low stress or the stress-free surface. So that are two deformation mechanisms that we really want to consider in this study. And all of these mechanisms, they are time dependent. So here, with the understanding of these two deformation mechanisms, here is how we pick these microstructural representations. So in this representative elementary volume, instead of just choosing the solid phase and the void phase, on top of this green and the void, we also choose the green boundary as the third phase. So here is a sketch of it, and we will have the mean field homogenization scheme. So there are two different conditions that we need to fulfill. The first one is the stress admissibility, and second one is the strain compatibility. You can see that from these two equations, how we link the microscopic or the inclusion behavior to the microscopic behavior. So here are two quantities, which is the microscopic stress and the microscopic strain, and we link it to the stress and the strain in the REV. So with these two fundamental equations, we're going to choose one of these homogenization methods, is so-called a self-consistent method. So this method is particularly designed for this material, such as the highlight, because it's a polycrystalline material, and there is no kind of like dominated material or dominated phase inside it. We consider each single crystal is embedded in so-called homogeneous equivalent medium, and we calculate the overall response by considering all different crystals inside it. And here, if we look at the bottom equation, that is a fundamental equation in this mean field homogenization relation, and tell us how to link the local behavior to the global behavior. So on the left-hand side of this equation, we can see that is how the epsilon, which is a strain in each inclusion, how this strain in each inclusion or the local strain deviate from the capital E naught, which is the average strain of this RV. So that deviation is linked by the linear relationship to the eigenstrain. The eigenstrain is defined as all types of the inelastic strain in this inclusion. It can consider as the plastic strain, viscous strain, or the thermal misfit strain, all this type of the inelastic strain. And in this linear relationship, we have a very important tensor we call the attribute tensor, which is S here. So it is a forcible tensor that can provide us with a linear relationship between the deviation of the strain and the eigenstrain or inelastic strain inside the inclusion. So that is the fundamental equation. And the first, as I just said, the first deformation mechanism that we want to consider is a dislocation. So here is a sketch of the slick system of this face-centered cubic crystal structure. And from this sketch, we can get the time-dependent and temperature-dependent strain rate relation as the equation shown here. So this is a viscoplastic strain rate, and it's dependent on the temperature and also on the stress that applied on this single crystal. So with this constitutive equation, we will consider the second deformation mechanism, which is a pressure solution. So here is I would say that is the innovation of this study, that we consider both the discontinuity of the displacement and also the discontinuity of the flux acting on the boundary. And we use this boundary phase or the contact phase to simulate pressure solution deformation mechanism. So we have this jump on the displacement and on the flex about this green contact, and we move down to an even smaller scale, which is a green contact scale. So here is a sketch of the model on the green contact, and we use the island channel interface model to model this pressure solution. So on this contact, it means that we have both solid to solid contact and solid to fluid contact. So here the first balance equation that we consider in this contact is a mass or the volume balance equation. It tells us that the mass dissolved under this pressure solution mechanism will equal to the mass expelled from the contact, and also the island increase, which is a solid to solid contact increase. So the first one is the mass or the volume balance, and the second one is, of course, will be the energy or the entropy balance. So in this equation, you can see that we consider that the mechanical work that input to this system or to the contact will equal to the three terms. The first one is the solid free energy change. The second one is the dissipation, and third one is the surface energy change based on because of the kind of like the solid trap in the contact, and the solid to the solid surface and solid to the liquid surface will change. So with all these two different boundary conditions, balance equations, we can consider build the constitutive model of both the solid particles and also the green boundary. So with all the descriptions of these local behaviors, the next step is that right now we have a local behavior, local constitutive model, and we want to link it to the REV behavior. So we have these fundamental equations. So this one is derived from the Escher-based equation that I just mentioned, and it's quite complicated, but overall speaking, it's a linear relationship that can relate the microstrain to the microstrain rate. So here the A is a first order tensor, it's so-called a strain localization tensor, and it contains information of both the solid part, the void part, and also the green interface part. So it can definitely give us information on how to simulate the pressure solution mechanism and the dislocation mechanism. So this is a linear relation, and with all this simulation, we also provide this linear relation for this diffusion problem. So that means in addition to this mechanical problem, we have this very similar phenomenon, at least from the formulation, it's really similar to the mechanical problem. And we're gonna have this linear relation that can bridge the micro concentration gradient to the micro concentration gradient. And from the bottom equations, you can see how it bridges the microflux to the microflux. So with all these equations, right now we have a local behavior, and we have the linkage between the local behavior to the global behavior. We can simulate it at a laboratory scale. So here is a recall of the sketch of this REV. We have this void inclusion, and we have also the crystal inclusion with the interface embedded in the homogeneous equivalent medium. And the simulation condition or the boundary condition for the simulation case is autometric test. That means we have no lateral constraints, and we apply the vertical stress. And we keep this stress constant, so it can actually give us a viscous behavior of the material. So the first thing is that we compare these results with, or we validate these results with some experimental data. So you can see that that is from the right figure. It's a comparison between experimental data and the numerical results. And you can see that our model can actually capture this stress sensitivity. And with a higher stress, we're going to get the higher volumetric strain. And it can also capture the influence of the different grain size of this salt rock, which can be found in the paper in detail. And with the understanding of the microscopic or the kind of like REV behavior in the lab, we want to kind of like focus on the microscopic perspective. So the first of all, we present here is a microscopic effective stress evolution. So you can see that from the left to the right, with the time evolves, this effective stress is actually decreased. The magnitude of it shrink a little bit. So here are two explanations of that. The first one is a healing on the void. So you can see that because the volume fraction of the solid increases, the micro stress, effective stress will decrease. And the second one, it can explain this observation is that we also have the healing on the interface. So we have the healing on the interface that causes the green boundary solid-to-solid contact increase. Therefore, we can get effective stress decreases. So that stress, the local stress or the effective stress, will actually control the behavior of the local inclusion and will therefore influence the global behavior. So that is the first observation from the microscopic perspective. The second one is not the mechanical response, but the diffusion response. So as I just said that because the solid-to-solid contact will increase, you can imagine that on the green boundary, the diffusivity will decrease with the time evolves. So from the left to right, you can see that the magnitude of the micro diffusivity on each contact will decrease. And here we see that, okay, the solid-to-solid contact increase on the green boundary. So that is actually the limiting factor for these pressure solution mechanisms. So that tells us, okay, this context or this context healing will prevent the pressure solution from continuing happening. So that is some observations from the laboratory and also some explanations from the microscopic scale. So if I try to summarize this study, you can see that we consider the two different deformation mechanisms explicitly, and based on the understanding of these two different time-dependent mechanisms, we pick or we select the different phases in our REV scale, in our REV. You can see that we choose the green boundary, the green and void. And with our understanding of the local behavior, with the understanding of the linkage between the local behavior and the global behavior, we can therefore get the quite good agreement with experimental data. And also we can explain why we will get such experimental data from the microscopic perspective. So this is the first material. The second example is granite, which is quite common in the rock mechanics. So here is also the motivation for this study. You can see that we have different scales of this granite, and we have from the micro image, we can see that we have different minerals, and we also possibly have the intergranular and intragranular cracks. And all these different types of minerals and different types of the cracks will influence the response of the representative samples that we test in the lab. And the performance of that will also influence the performance of the geothermal structure that build upon this granite. So this is the different scale separation of that. And we again ask the question, what kind of like the phenomenon that we really want to simulate in this study. So it's quite different from the other studies in the granite that we want to consider the weathering effect here. So here we only consider one mineral weathering, which is called biotite. So under the weathering, the biotite will transfer to other minerals and the volume of the biotite will expand. So you can imagine that because of this expansion, it kind of have some misfit strain. So that is also the eigenstrain that we just explained. So that is one type of the inelastic strain. So that misfit strain will possibly cause the microfracture or microcrack propagation. So that there are two different mechanisms that we want to consider: the biotite expansion because of the weathering, and also microcrack propagation because of the weathering. So you can see that with the understanding of these two deformation mechanisms, we're going to have this representative elementary volume, and we consider two different types of the inclusions. The first one is the biotite inclusion, and second one is the crack inclusion. The biotite inclusion is used to simulate the biotite expansion under the weathering, and the crack inclusion is used to simulate the microcrack propagation in this study. And here we use a slightly different method from the method that I just mentioned, which is a self-consistent method for the polycrystal material. So in this study, we actually focus on the biotite. So that means we have a dominant mineral that we want to focus on, and all other minerals, we consider them as a matrix. So we can consider the biotite and the crack are embedded in this matrix. So that means the Mori-Tanaka method is more suitable for this study. But the fundamental equation for them are similar. It's just the exact, like the detailed formulation for the Mori-Tanaka method and self-consistent method, they are slightly different. And also the solving algorithm are slightly different. So for the first mechanism, it is the biotite expansion, as I just said, and we have the eigenstrain or the misfit strain. So here I provide the exact formulation for this eigenstrain, and this eigenstrain is really dependent on the volume change of the biotite to other minerals. So that is a local behavior for the biotite inclusion. And on top of that, we give the thermodynamic based model for this whole REV to consider the combination of the biotite weathering and also the crack propagation. So here in this free energy of the REV, you can see that we generally have three terms. The first term is traditional term, which define the deformation energy. And here the C homogenized is a homogenized stiffness tensor, and E is a global strain tensor. And the second term is the eigenstrain, which define the contribution from this biotite expansion under the weathering. And third term is actually the coupling effect. So it tells us how the crack propagation and the weathering coupled with each other. So with this free energy formulation, we can easily get the driving force for the micro crack propagation, and by taking the derivative with respect to the crack density. And also we can define the second order damage tensor as a directional summation of these crack density variables. So that is overall like the tensor, which characterize the internal variables. And here we will have this local constitutive behavior. The first, the top equation is the local constitutive behavior of the biotite. So it has two terms. The first one is the elastic term, and the second one is inelastic term. So that is corresponding to the eigenstrain, and we define it as the eigenstress term. And the second equation on the bottom equation, you can see that is the kind of like the relation between the local behavior, the microstrain, and to the microstrain. So still, it's very similar to the content that I introduced before. It's a linear relationship, and it has a fourth order tensor A, which is a strain localization tensor. And on top of that, it has a second term on the right-hand side, which defines the contribution of the eigenstrain, how the eigenstrain or the biotite expansion in each biotite inclusion will influence the overall response. So with these two equations, we have, it's kind of like the two-state molecular homogenization, because the crack inclusion and the biotite inclusion, they are different type of inclusion. So in order to avoid any like the mistakes in the stiffness tensor, so we have this two-state homogenization mechanism, homogenization scheme. So the first step is that we actually calculate the crack inside this undamaged matrix, and we calculate the anisotropic stiffness tensor for this damaged matrix. And the second step is that we calculate the biotypes that embedded in this damaged matrix. We get the finalized homogenized stiffness tensor, which is the C homogenized here. And that is also the value that enter into the free energy of the REV that I just mentioned. So here is a sketch of this material point study. You can see that we consider random distributed crack inclusion, and we consider the aligned biotite inclusion to investigate influence of the different biotite orientations. So that is the study that conducted on the material point simulation. So with this simulation, we trying to implement it into the one of the finite element solver, which is Abacus, and we use a user-defined material subroutine to do that. And here, that is a general kind of a cycle of how we solve for this finite elements simulation. We have the internal state variables. We have two types of internal state variables. One is D, which is the damage variables that define the micro crack propagation, and so epsilon C, which is a chemical like strain or the eigenstrain that associated with a biotite expansion. So with these internal state variables, we will have the global residual, and we solve for that in the Abacus. So here I will present some results that we simulated in this finite element solver. So you can see that for this field scale simulation, we have this kind of topography, and that is a sinusoidal free surface, and we have the body force and the lateral earth pressure. And on the bottom figures, you can see that we have two different patterns of the applied weathering. So I want to emphasize is what I want to emphasize is that the boundary condition here, the stresses are constant, and the only driving force for the deformation is the weathering. So we imply the weathering with the different patterns of the two different types of the weathering patterns, and more importantly, we have this increase the weathering rate towards the free surface, which is understandable because the free surface, the top surface, kind of have more contact with the environment, and we can imagine that the weathering rate there will be higher, and it goes lower and lower towards bottom of this geometry. So with this study, the first observation is that how the damaged components or how the microcrack propagate under this condition with this biotite weathering pattern. So you can see that from this figure, comparing the top figures give us the normalized damage or the damage component. You can understand it as the magnitude of the microcrack propagation. So before weathering, it's actually not that damage accumulated, but with the weathering after the 1,000 years, you can see that damage pretty much accumulated follow the pattern of the biotite weathering. So you can see that from this, we see that probably under these simulation conditions, the biotite weathering is a control factor for the damage accumulation in this geometry. And with a different orientation of the biotite, you can see that if the biotite is aligned vertically, we will get a greater value of the damage. So that is because kind of like complete conflict between this biotite expansion direction and also a lateral pressure. So that is the one observation of the damage components after 1,000 years of weathering. And we also want to see how the stress alternation after this weathering. So you can see that if we compare the results before weathering and after weathering, the top figure and the bottom figure, we can see that the biotite weathering indeed altered the distribution of the stress, either the horizontal stress or the vertical stress. And you can see that because the boundary condition, the stresses that we apply on this system are constant, and this stress alternation is driven by the biotite weathering and the microcrack propagation. And you can see that with the different biotite orientations, we will get different patterns of the horizontal stress and vertical stress. And with the the vertical aligned biotite, we'll get the more alterations in terms of the stress distributions. So that's all the kind of like above simulations. It's a simulation that we apply or we predefine the weathering pattern. And the second simulation cases that I want to simulate, it's that we want to consider not only the micro crack propagation, we probably want to consider large fracture propagation in this study and how this fracture propagation will coupled with the weathering front propagation. So here we use we also use abacus to simulate, and we use a user-defined material to simulate the bulk element, which is the granite element, and we use a user-defined element to simulate the cohesive zone element. So, and on top of that, we also consider the information change between the bulk element and the cohesive zone element. So first of all, we consider that the microcracks and the weathering in the bulk element of this granite will influence or will degrade the strength of the cohesive behavior in the neighboring cohesive element. And the cohesive element, once the fracture propagates, it actually can initiate the weathering. So we have this kind of like information exchange between two different types of the elements. And it can actually help us to predict the feedback effects between the weathering and the fracture propagation. And it can also help us to simulate the weathering front, how the weathering front moves. And here I show the two different boundary conditions for these simulation cases. You can see that the geometry are pretty similar to the previous simulation cases, but on top of the lateral earth pressure, I also apply lateral tectonic stress. So in this study, we really want to investigate the effect of both the topographic stress and also the tectonic stress. And the difference between these two different simulation cases is that the left one, we didn't really insert any fracture. So we have this kind of like geometry, and we have this applied tectonic stress, and we use that to initiate the fracture, and then fracture will initiate the weathering. And on the right figure, we actually insert pre-existing the fracture zone, and this fracture zone will initiate the weathering, and then the weathering will degrade the stiffness of the solid, and then the weathering gonna propagate. So that are two different cases. And the first simulation is the field variables at t equals 0. So that means at the moment that we apply all these boundary conditions, we can see that the combination effect of the tectonic stress and topographic stress, and how that initiates the fracture. And with that, you can see that for the left column, which is the no tectonic stress. So that means only lateral stress is the lateral earth pressure. And under these simulation conditions, you can see that the lateral earth pressure is not sufficient to open any crack in this simulation case. And on contrast, for the tensile tectonic stress and compressive tectonic stress, the simulation condition can open the crack under the valley, but with a different pardons. For the compressive tectonic stress, it tends to open the tensile and shear fractures, while for the tensile tectonic stress, it tends to only open the tensile fractures. So that is at the moment before the weathering or the fracture propagation, before the weathering happened. And then we can see that how this weathering fracture zone evolve with the time evolve. Sorry. Yeah. So in these slides, you can see that it's from the 50 years to 100 years and to 250 years. So you can see that for the compressive tectonic stress, the weathering regions, it tends to spread laterally beneath both the valleys and ridges. And on the contrast, for the tensile tectonic stress, the weathering front advanced deeper under the valleys. So those observations are consistent with observations in the field for different tectonic stresses. And with the, if we inserting this kind of like pre-existing crack zone, we can see that how this pre-existing, if we compare these results with the results from the left side, we can see the influence of this pre-existing crack zone. You can see that under the compressive tectonic stress, this predefined fracture zone has a little effect on the overall performance, but for the tensile tectonic stress, it can progressively give us a wider and a deeper region beneath the valley floor. So that is a comparison of the cases without the pre-existing fracture zone and with the pre-existing fracture zone. So all these observations are I would say that qualitatively consistent with the field observation under the different tectonic stress condition. So if I try to summarize this study, that's quite different from the part one, because the part one will only focus on the complicated behavior on the RUV scale, and we only provide the material point simulation on the RUV scale. In this study, we actually do the three different scales. The scale at the microstructure, we consider biotite expansion, and we consider microcrack propagation. The scale at the RUV scale, we use a UMAT to implement it into the finite element solver, and to solve the problem, boundary value problem, or the large scale problem. And we also combine this kind of like the bulk element and the cohesive zone element to simulate the fracture propagation. And we consider these feedback mechanisms by considering the information exchange between the bulk element, the solid element, and also the cohesive zone element. So that is kind of like the graphic summary of the phase two, the part two. And I have the kind of like a little bit summary of the contributions of the highlight model. So in terms of the application, we see that the model can actually be able to capture the self-healing mechanism, and it can also give us explanation why the green-to-green contact healing is a limiting factor of the pressure solution mechanisms, and how all these limiting factor will influence the overall response that we observed in the laboratory. And in terms of the theoretical part, it's actually not limited to the application to the highlight, but it's provide a pretty general homogenization frame for this kind of nonlinear and time-dependent problem. And it can also consider the jumps of the displacement and the flux inside this problem. That is pretty innovative. And with that, this model framework is expected to simulate all other similar phenomena, such as the green boundary debonding, sliding, elevation, and diffusion transform. So we can expand this model to consider other problems. And for this second part of the granite, we, as I just said, that we are not limited our study in the material point integration point scale. We actually implemented to consider a large scale problem. And we also investigate how sensitive of this microcrack propagation to this weathering process. So that's all these observations are pretty consistent with the field observations, so which are quite exciting. And in terms of the theoretical part, first of all, at the material points scale, we use the two-step Moritaaka method to consider both the microcrack propagation and also the biotite expansion. And on top of that, we're using a thermodynamic-based model to consider how the microcrack propagate based on this driving force. And by combining this bulk element and also cohesive zone element, we can actually simulate the feedback mechanisms between the weathering front advancing and also the damage propagation. So that will conclude the talk today. And I have the acknowledgement. Basically, it's the research groups that I stayed. So the master and PhD and the postdoc. And I really appreciate the experience with them. So I'm happy to take any questions if you have.
Okay. Thank you. Thanks for this speech. If any audience have any question, please feel free to directly unmute yourself and ask the speaker.
Thank you very much. A very nice presentation, Tingting, and it's a very wonderful work. I have one question related to the Ashby tensor stuff, because in your conclusion you mentioned about the homogenization of the consider the viscoplastic, but in the tensor stuff I didn't capture where the viscoplastic can be quantified.
You mean in the basic equation that I showed before?
Yeah, because I see that only elastic linear relation.
Oh, yeah, this one is actually, yeah, you mean this one? This one is actually the traditional one of the linear elastic. But I in my formulation, I actually have two terms. So for both the elastic and the viscoplastic part. So
okay, so viscoplastic is added in your formulation. I see.
yes, that's true. So we have two different types of the Ashby's tensor.
Okay. Another point is the pressure solution stuff is time dependent, right? The process.
Yeah.
So which part is considering the time, the time dependent stuff, the process?
So if you look at this, yeah, I didn't show in the slides, I think. But you can see that it's very similar to this dislocation. So dislocation, we have the viscoplastic strain rate that
Oh yes, here, yeah.
So in the pressure solution part, at the end of all this simulation, all these balance equations, I also have the viscous strain rate that related to stress. So they share a very similar formulation. So that's why we can cascade into the viscoplastic Ashby formulation. So that means with the constant stress applied, I can also have the pressure solution happen. So that's how we explain this is a time-dependent behavior.
Okay, great. Is it coupled with the pore pressure so far in your simulation? Not yet. It's very tricky to include.
Yeah, that's gonna be very tricky.
Yeah.
You didn't consider the pressure inside the void. That's a little bit complicated. But the pore pressure it has a term in the formulation. If you go to the detailed formulation in my paper,
Okay.
but it's not that like um, how to say the completely considered in this problem. I didn't consider the pore pressure change, or the eigenstrace change inside the void inclusion.
Okay, wonderful. Thank you so much.
Thank you.